We've said several times, and you've probably encountered the idea before, that the temperature of a system is a measure of the average kinetic energy or the average velocity of particles in the system. But what is that relationship? To answer our question, we're going to have to think about how we find averages. So let's look just in general at how we would find an average. So if we have 5 people and each person has a different height, and we want to find the average height of those 5 people, we're going to add up the height of each person and divide by the total number of people. So we have 2 people that are 6 feet tall, so 2 times 6. We have 1 person that is 5 feet tall, so 1 times 5. And we have 2 people that are 4 feet tall, so 2 times 4, divided by the total number of people, which is 5. That should give us the average height. We can rearrange this equation and write 2/5 times 6 plus 1/5 times 5 plus 2/5 times 4. Notice that the fraction that multiplies the height of the person is the probability that someone within these 5 people has that property, is 6 feet tall. So 2/5 of my people are 6 feet tall, and the probability of having someone 6 feet tall in my distribution of heights is 2/5. So if I take the probability of finding that property times that property and add that up for each different value of the property, I should get the average of that property, which in this case is the height. So if we write that out in general then, the average height can be calculated by taking the probability of height 1 times that height, the value of that height, plus the probability of finding height 2 times the value of that height, plus and so on, till you add up all the different heights, or the average height is the sum over all possible values of the height times the probability of finding that height times the value of that height. Now, if we have a continuous distribution, as always, that sum becomes an integral. And so the average value of a property will be the integral over the range of the probability of finding that property times the value of that property integrated over all values of that property, x. Let's take that definition of an average and apply it to our probability distribution for the velocity. Let's see if we can find the average velocity. So if I want the average velocity, I'm going to take the value of the velocity times the probability of finding that velocity. So I have my Maxwell-Boltzmann distribution probability here. And I'm going to integrate over all possible velocities. So first, let's combine our velocity terms into a v cubed term here. Now the best way to do this integral is to do it by parts. So I'm going to divide my integral up into a v squared part and a v times e to the minus mv squared over 2rt times dv part. I'm choosing those parts because I know how to integrate this. And when I integrate dx equals v e to the minus mv squared over 2rt dv, I get x is equal to minus rt over m e to the minus mv squared over 2rt. You can verify that that's the case by taking the derivative of this and showing that you get back dx. Now, when I integrate by parts, I'm going to take x times y, evaluated over the limits of my integral, minus x dy. So minus a minus gives me plus x dy, 2 rt over m, which are constants for this integration, v times e to the minus mv squared over 2rt dv, integrated over the limits of my integration. Notice that I've removed the 4 pi 3 halves m over 2 pi rt because all of those are constants of integration, and I've removed that from my integral before I wrote out my integration by parts. Now let's evaluate this first part from 0 to infinity. So I'm going to plug infinity in for my velocity. And I'll notice that infinity squared is still infinity, but e to the minus infinity goes to 0. So the question is, what's infinity times 0? Well, this goes to infinity as the square, whereas this goes to 0 exponentially. So this goes to 0 much faster than this goes to infinity, and so this guy wins out, and that's equal to 0. So when I plug infinity in, I get 0. Then I'm going to subtract a minus whatever I get when I put 0 in for the velocity. When I put 0 in to the exponential, e to the 0 is 1, but when I put 0 in for v here, 0 times 1 is 0, and so I get 0 minus a minus 0, and so I get 0 for this term. Notice that this integral is exactly the same integral that I did up here. So I already know the answer for this integral. So combining all of my constant terms and writing out the result of my integral evaluated from 0 to infinity, when I do that, I get the following. So I'm going to do some algebra. You can follow through this algebra, and what I end up with is that the average velocity is related to the square root of the temperature and the square root of the molar mass of my particles.